Hi, I'm Mr. V, and today's lesson is from Illustrative Mathematics, Unit 2 on Congruence, and this is Lesson 5, Points, Segments, and Zigzags. And before we get into the lesson itself, I'd like to go through one of the homework problems, which will play an important part in what we're talking about today. One of the homework problems from the previous section, which is extends into what we're going to be talking about today, says that a rotation by angle ACE from here to here, using point C as the center, takes triangle CBA onto CDE. Since it is a rigid transformation, that means that this triangle is congruent to this triangle. Now we are to explain why the image of segment CB, the image is after its transformation, must line up on ray CD. It doesn't say that it lines up at CD, it says it lines up on this ray. And if I rotate this from angle ACE around point C, that means that I'm rotating this by the same degrees. And we know that a rigid transformation is either a translation, it is a reflection, or it is a rotation. And rigid transformation takes lines to lines, segments to segments of the same length, or angles to angles of the same measure. So if we're going to go this angle of the same measure, this will guarantee that point B will be on this ray because it has to be at the same measure as the original. So this has got two parts. The first part is that, the first part is that when we rotate, we're ending up with the on the same ray. The second part of this is why then do you know that B matches up with D? I'm going to say that point B is a segment of this length. When we do a rigid transformation, such as a rotation, it takes segments to measure segments of the same length. Now, because it is rigid transformation, it's going to be the same length. That means that the distance from C to B prime, my rotated version, is going to be the same distance along this ray, which we know is the same, as D is, because they're the same length. So B prime and D must match up. The second part of this is that when you do the segments of the same length, they have to match up because they're on the same ray and they're the same distance from the endpoint as the ray. And you will see this again in today's lesson. So today's lesson is from Illustrative Mathematics. We're on lesson 5. By the end of the period, the goal, and if you get this goal, you're golden. If you understand this, I can prove that segments of the same length are congruent. That's what we're trying to do. You should try each of these before watching this video. If you would, try them first. First of all, a point A is a point in the plane, point B is a point in the plane, then A is congruent to B. We want to prove this. Claim by explaining why you can be certain that the claim must be true. Or to disprove it, you can write a counterexample, which is explain why it can't be true. That is, a counterexample is if you have an if-then statement. If point A is a point on the plane and B is a point on the plane, then A is congruent to B. If the if part is true and the then part is not true, that is a counterexample, if you can draw that picture for us. And you should try to do this. Now, I'm going to do it on a picture here if I can find a... Here we go. So here I have 2 points, and I'm going to show you, well, what does it mean to be congruent? The definition of congruence is that one object, a pre-image, can be mapped onto a second object, the image, by a finite set of rigid motion transformations. So if there's a rigid transformation that takes point A to point B, then you know that point A and point B in a plane are congruent. So the first thing I would do is I could translate. I could translate from point A to point B. When you translate, you have to have what it is you're translating, point A, where it's going from point A, where it's going to point B. This is my directed segment. That's what you need to do, translation. To do a reflection, I need to define the line of reflection. So I could take point A and point B in this segment and find its perpendicular bisector. So the line that is perpendicular to these two, and it's going to be through its midpoint. This, if I reflect across this perpendicular bisector, this will take me from point A to point B. There's a rigid motion transformation that takes me from A to B. That means that they must be congruent. A third way of doing this rigid transformation is if I found the midpoint between these two, M, and you rotated point A around point M 180 degrees, then it would take me from point A to point B. So there's a rigid transformation that takes me from A to B, which defines congruence. The pre-image can be mapped onto the image with a finite set of rigid transformations. Now, when I do a rotation, I have to define the point of rotation, the degrees of rotation, and the direction, unless it's 180, in which case it's moot because it's the same either direction. If I do a reflection, I have to define the line of reflection. Here I'm saying it's the perpendicular bisector. And then if I want to do a translation, I have to say, translation. I'm going to say, I'm going from point, what is my directed segment? I'm going from point A to point B. So, going to the next page, activity synthesis. It is true. The two figures are congruent. 2 points are congruent, point A and point B in a plane. Two figures that are congruent, there's a rigid motion transformation that takes the one exactly to the second one. For example, translate A to B using a directed segment from A to B. Reflect across the perpendicular bisector, or rotate 180 degrees around the midpoint. And remember, when we translate, we have to define the directed line segment. When we reflect, we have to define the line of reflection. When we rotate, we have to do three things: the point of rotation, the degrees of rotation, and the direction of rotation. Okay. Now, here is the next statement. It says, if AB is a segment in a plane and CD is a segment in the plane, then AB is congruent to CD. Prove this statement by showing a series of rigid transformations that take segment AB to CD. Or give a counterexample. Again, a single counterexample disproves a claim, or a single counterexample in which the if part of the hypothesis is true, but the then is false. That would disprove a claim. And you try doing this, and I'm going to show you how I would do this using trying to make this here. Here are two segments, A, B, and CD. Are they congruent? Is there a rigid transformation that takes one to the other? I'm going to define a transformation. I'll do a translation from A to C. And I'm going to translate this segment by that much. I'll color this orange so as to distinguish it. The orange is what I've just translated. Now I need to rotate it. How many degrees? Well, I'm going to measure from this angle. I'll go 44 degrees in a clockwise direction. So I'm going to define the transformation of a rotation around point C by not 90 degrees, but I'll go by 44 degrees. And since it's in the counterclockwise direction, I'm going to make this negative because a positive is in the counterclockwise. If I want to make it go the opposite direction, I'll make it a negative. And now I'm going to apply that to this segment. And when I do, there it is. It matches up. It's on this ray. What? It's on this ray. My A prime, B prime, A double prime, B double prime is on ray CD because I went this many degrees. Why don't these points match up? What's wrong with this? Well, duh, they're not the same length. We know that when you do a rotation, it's going to go on this ray. But when we do a rigid transformation, it takes segments to segments of the same length. Since this didn't start off with the same length, it's not going to match up. And remember from our earlier discussion here, where is it? We have two things. You have to rotate, make sure it's on the same ray, and then the segments of the same length. So that's what's important here. Now, going to the next page. The original statement was, if AB is a segment on the plane and CD is a segment on the plane, then AB is congruent to CD. And I just showed you that that's not necessarily so. I gave you a counterexample. How could you reword this to make it sure that it's always a true conjecture? We could say, if AB is a segment on the plane and CD is a segment on the plane with the same length, then as AB, then AB is congruent to CD. And that's what we're going to prove. Now, in this class, we make assertions. We think something's true, and then we can test it out a lot of different times. So we make a conjecture. We think this is true, and then we can prove it or disprove it. Like we just disproved the original statement, we can prove this statement, and if we prove it, then it becomes a theorem. So assertions become conjectures, become theorems. Now we've got a conjecture. This is a good conjecture, and we want to make it into a proof. We could do proof by contradiction. I'm going to ignore that for now. I'm going to do this one, and I'll show you with my full screen again. So I want to map this segment with the same length as this segment to prove that they are congruent. And I would write my steps over here as I did it. First thing I'm going to do is I'm going to translate. I'm going to translate from A to C. What am I going to translate? I'm going to translate segment AB from A to C. And again, I'll make this a different color so you can see it. I need to rotate it by an angle. Well, I need to measure the angle. So to measure the angle, I will just use my construction tool and measure the angle at 65 degrees. And now I want to transform this by rotating around point C. When I go, so I need to define the transformation, a rotation around point C of 65 degrees, but it's not going to be in the counterclockwise direction. It's going to be the clockwise. So I need to make this a negative 65 degrees. What is it I'm going to rotate? I'm going to rotate this A prime B prime, A prime B prime. Apply it, and it matches up. And lo and behold, my A double prime, where I've rotated this, matches with D. Why? Because segments, first of all, I know that when I rotate it, it's going to be on this ray CD, but I know that this segment, which was 4, when it's got a rigid transformation, a rotation, it will be the same distance from C as D is, because they takes segments to segments of the same length. And that's why. So there's 3 parts to this. One is the translation, next is the rotation, and then next is to point out that because the segments have the same length, that it's not only on the same ray, it's also the same distance from the endpoint of the ray, making these two congruent. And that is a proof, folks. That is a proof showing that if I have 2 segments in a plane of the same length, then they are congruent. And we're going to use that. Now you could do some more with this. You could say if I have 2 strings and they have the same length in a plane, then they are congruent. Is that true or false? And you could draw one like this with a squiggle, and the other one like this, almost straight. No, it's not true. They might have the same length, but they don't have to be the shortest distance between 2 points. A segment is the shortest distance between 2 points, and that would be like a straight. And they don't have to be straight if they're a string, so no, it doesn't have to be. Activity synthesis. You need to add this to your reference chart. If you're missing the reference chart, I've added a link on page 14 where you can go and you can copy this or download this. This is what you're filling in the blank. We will use this reference chart for the entire course, not just for the first half, but for the entire course. Here we have, if 2 segments have the same length, then they are congruent. Well, duh. No, don't well, duh me. This is not trivial. This is going to be something that we will use in other more rigorous and more difficult, more challenging proofs. If we start off with 2 segments that are congruent, that means that we can map the one onto the other with some set of rigid transformations, maybe a translation and a rotation. Now, Zig-Zag. In this activity, you could work with a partner. You could try to doing this yourself. Here are some statements about a zigzags, QRS and XYZ. We want to prove that with this side, angle, and side, this 2 sides and this included angle, that these 2 are congruent. And your task is to order these. I will show you how we do that soon. You can try doing this with this with this GeoGebra app. You can try rotating these and translating them and doing this. We're going to go ahead and we would state how we would do this here. Lesson synthesis. This is what's important. Let's see. There's some sentence frames here that you can use for justification in proof. You might want to make a note of these and maybe even copy this down and put it in an important place. In the lesson synthesis, this is where I describe the proof for you. If two figures are congruent, there's a sequence of rigid motion that takes one figure onto the other. We can use this fact to prove that any point is congruent to another point. We can also prove that segments of the same length are congruent. And if you get that part of it, you've gotten the lesson for today. That's the big part of the lesson today. But finally, we can put these arguments together to prove entire figures are congruent. So these statements here below prove that ABC is congruent to X, Y, Z. Segments AB and XY are the same length. So they're congruent. That's what we proved in this lesson. Therefore, there's a rigid motion sequence that takes AB onto XY. Apply that rigid motion to the figure ABC, whatever that rigid motion transformation is. If necessary, we have to reflect the image of figure ABC. The image of the figure ABC is what it is after you've translated and lined them up. We might have to reflect it across XY to be sure that the image of C, which we'll call C prime, is on the same side of XY as Z. So if we have to reflect it, C prime must be on ray YZ. Why? Since both C prime and Z are on the same side of XY, and they make the same angle at Y. So they're on the same ray. In this fourth point, since C prime and Z are the same distance on that ray from Y, from the endpoint, they have to be in the same place. Therefore, the figure ABC is congruent to figure XYZ. That is, we started off by taking the two segments and lining them up. That lined up two of the vertices. The trick was in the step 3 and 4 to line up the third vertex. When you line up all three of these endpoints, these 3 points, then that's the way that we can prove that the two are congruent. Wow, a lot of stuff here. For the cool down, any two circles in the plane are congruent. Do you agree with this? If you do, tell me if you agree with it. Tell me if you disagree with it. If you agree, explain how you know. If you disagree with it, I could say draw a counterexample. But if you disagree with it, I want you to edit the conjecture to it so that it will always be true. Maybe the sketch will help. If I were doing this, I could say, I have a circle in a plane. Here's one circle. I'm going to draw it with the center. There's one circle. Oh, and here's another circle. They have the same center. They're concentric. Are they congruent? No. What has to be true for them to be congruent? So this is my counterexample to say that no, that's not true. To be true, I would have to have circles of the same radius. So if I had a circle with this radius, and I had another circle with that radius, then, so any two circles in a plane with the same radius are congruent. That would be correct. And please tell me how you're feeling today, and good luck and success.